So, we are ready for the keynote. I probably should move closer to the mic that everybody can hear me. So we are ready for the keynote, and it is my really great pleasure to introduce Moti Young. I think everyone who is in the security community knows Moti in one way or the other. He provided me a bio, and it's very modest for all of the things he did. He's currently working in the security and privacy team at Google. He got his PhD from Columbia University, then started his career, I think, at IBM, moved through a number of companies. I think I first came across him when he was working for RSA, then went to Google, went briefly to Snap, went back to Google. He received very many awards, the IEEE Computer Society 2021 Computer Pioneer Award, the 28W Wallace McDowell Award, and this is very important. In 2014, he received the ACM SIGSAG Outstanding Innovation Award, and if you have been at that event, he presented actually that he established the first business use of private set intersection and multi-party computation at Google back then. And this is a real milestone for all cryptographers that these technologies are actually being used in practice. And I know that Moti has a whole bunch of surprises for us today, I'm sure. And I'm sure that there will be another set of very interesting technologies that Moti brought about. And I'm really glad he shares those with us. He also received the ESORIX Outstanding Research Award and gave in 2010 an ICSR Distinguished Lecture. He's a fellow of ACM, IEEE, ICR, EATCS, and an interesting tidbit of his bio is that he has more co-authors than days in a year. So he probably has more co-authors than people have registered here for the PETS conference. So this gives you an idea of how long Moti is in this game, and we're really glad to have him. So with further ado, Moti, please you can start your keynote. Thank you very much. Welcome, Moti.
Thank you very much for the kind introduction. Do you hear me? Do you see the slides?
Yep, loud and clear.
Do you see the slides moving?
We see the first page still.
Still the first page. Do you see the second page now?
No, unfortunately.
A second. Okay, now you should see. I moved slide, you see?
No, we can't see anything currently. So same steps as before. The bottom left corner, there's a little screen icon. Click that. Probably share your display instead of just the PowerPoint.
One second. I do a screen share again.
Yep, we can see the PSS research Google. It is changing.
Yeah, it is changing. Okay, great. So first time I use this system, and it's fun. So I will talk today about privacy integrated computing cryptographic protocols in practice. And this is joint work with people in Google PSS, Privacy, Security, and Safety Research, and Google research teams and other people sometime, but mainly people in the industry. PSS is a newly reorganized research group dealing with privacy, security, and anti-abuse in Google to support the PSS group, which is essentially the security engineering teams in the company. So the agenda. I will start by characterizing the typical computing situation nowadays. I would then demonstrate that such computing nowadays is needy of privacy-enhancing technologies. This will be concrete industrial projects of leading companies that are moving like Google in similar directions. I will point at what I think made these projects successful and how following some principles, like I'm mentioning, can help the industry and also help technology transfer in general. My goal is not to show you my more recent and fresh research and show a lot of muscles of cryptographic technologies, but rather to draw conclusions of what works in practice and why. And this project and other projects by other people, I think, will set the direction of privacy in the coming future. And this is the important one, the important outcome of this talk. It will be more like conclusion drawing based on technologies and based on some technologies, even though these technologies that are presented in the past, but the perspective of post deployment and post successful deployment and extensions will be very important, I think, to this community. After all, we are talking about a success of basic research agenda that is the core of this conference. So computing in the last 50 years, to typify it, I went to see the vision of Doug Engelbart. He viewed computing as an extension of human activities. He's a Turing Award winner. He's known colloquially, but he's done more than inventing the mouse, which is a very important interactive tool for computing. But he characterized computing, the goal of computing, boosting mankind's capability for coping with complex and urgent problems. And later on said, augmenting society's collective IQ. So helping humanity coping with emerging complex issues is a big part of the foundations of computer science have to do. And this is its outer-facing challenges when facing users and facing other fields, facing other areas of what humans are doing. And we can see it when we analyze how computing and humans are getting closer and closer in some sense. In the 80s, there was the PC revolution. So suddenly people got a desktop and they could use it in their office or in their home office. And we saw many of the functions that used to be on the office desk moving into the PC, like printers. And then came the internet. Suddenly there's global reach. People get their news, their mail, and social interactions, and buying, and shopping, and publishing. And you can do it. And then we saw the mobile computing ubiquity. Everywhere you go, you have a computer with a smart computer in your hand in the last 10 years or so. Your your wallet is now while computing maps, car rides, and so on. It's all in your pocket and it's a computer. And then came cloud, which gives you vast, flexible, elastic resources as you need. And we see the IoT coming, devices everywhere, and now you control everything with computing. So indeed, computing has become a human reality and serves human needs very well. So Engelbart vision is really in full swing, and we cannot envision human experience in modern life, or we cannot almost not do it without a computer. I mean, it doesn't mean that we take breaks and go hiking in the woods, but in general, for the long run, we need to interact somewhat with computers. So, so computing is about people, it's with people, but I quote Yogi Berra here, who said a lot of interesting things, contradicting things, but he said if the world were perfect, it wouldn't be. He said he didn't even understand self-reference, but he said it anyway. He's known for such things. And what do I mean by this? Where is the imperfect situation? So, as individuals are served, their data is necessarily being used. So somehow there is an exposure. And this immediately assures that privacy is part of what computing needs, because as you share your data, you don't mean to share it with everyone. You don't mean that your privacy needs to be violated. So as computers and humans get together, obviously human data is used and privacy pops up naturally. And this happened, to be my thought, in 2007 as I joined Google. At that time, many in the security community thought that crypto research is over because they had SSL. So it's all done. Everything they needed for secure internet was there. There was SSL, there was AES, there was MD5, never mind it was later broken, and there was RSA. So they could do everything. And Web 1.0 was very successful. It became the center of the universe. And 2007, I still remember myself thinking the game is just beginning. Many challenges around, and technology is bound to change soon. And privacy was one of the main motivations due to already that human and computing are together, and data is in the mix, and we don't want to give away data. All right? So, I don't know, I called it at some point privacy integrated computing thesis, and many people contributed many ideas to this thesis. The short way to think about for this community is that privacy should be built in wherever possible. And now I think perhaps beyond privacy by design, privacy is something that should be maybe part of this, even the specification. You deal with data, and the data has to be characterized somehow. So it's not necessarily that it's just you add privacy, enhance with privacy. The design, you may even in the specification qualify which data and what data and who gets what. And it's perhaps beyond privacy by legal requirement, which was one of the originating motivation for privacy, because privacy is a technical built-in regardless of the current law. The law can change. So, as I say, think about privacy from the start. And it's actually easier than retrofitting privacy. It's the same thing of thinking about security. If you want to build a system based on data and you design certain blueprint and principles and partially implementing the specification goals of privacy, it's much better to retain privacy and extend privacy than if you build it without privacy and then you have to take care of privacy. Same as principle that is well recognized in security research. Obviously, law, policy, etc., are important. Any modern computer scientist who works in practice has to interact with these fields and similar fields because of again, this is because human activity and computing are becoming are overlapping and all becoming the same. Of course, but in this talk I will not stress law and policy. I have other talks for it. One thing I want to say is that we may not get to this privacy integrated computing in one shot. We may need to iterate, we may need to trade it against utility, but the goal of modern human-centric computing should include privacy. And what I want to show you today is some good news about privacy and the current wisdom of people I interact with. So people believe now that computing is about big data, and we, not always, in many situations, we do not need individual data. And the industry started to attempt to keep user data privacy while working only on aggregate. It is considered sometimes liability to keep too much information. Sometimes user to server data sharing is reasonable because the user wants some task to be done at the server. But collecting data about the users from anywhere it is on the internet, when it is not authorized by the user and it's not something that the user expects, and it's something that is there by accident just because of cookies being the way to keep state when a user gets an internet is now people start to think it's not warranted. When we need only limited information on an individual, there's no need to carry all their data. As I said, it's potentially increased liability. And some people think, we need the individual data only on a need-to-know basis. And I will try to demonstrate this type of thinking and implications in the techniques that I will present. So the first example that I will talk about will be the continuation of the 2015 talk that I gave in CCS about this technology that was mentioned by Florian. But finally we took the theory of secure computation and put it in a big company for daily routine and important tasks, and I use it to draw some perspective. First, how it evolved over the years, and how what are the principles that allow this success, and how important it is to have the first success. So I have a slide here which says secure computing, why now? So the internet electronic business is a multi-company cooperation between different corporations. And these days people talk about machine learning with data from different sources. Now we have cloud, which hosts data, and the users may not want to give all their data to the cloud and in plain text form. And we have Internet of Things, small devices that you need for help, but they are very personal and they may reveal things about the user. So there are existing and coming technologies that really demand this secure computing or privacy enhancement. And the first with internet e-business being multi companies who hold the data about users was my first motivation, but all of the bullets above at the top of the slide apply now. And to many of these situations, other alternatives which do not include secure computing as a component, at least, don't work. And privacy enhancement and cryptographic protocols are now over 40 years in existence, and we have packages that run it and so on, and cryptography that is more or less, at least more debugged than in the past, and it seems to be possible. So when I started it, just as an innovation, as a social and tactical choice, I wanted to employ privacy enhancement to offline computation. I had cryptographic solution in mind, and cryptography requires some overhead, but at least for the initial demonstration, offline is fine and can tolerate some validity. It was important that it will be an essential task, critical to the company, because I didn't want just to solve a problem. I wanted to change minds that privacy can be achieved. Privacy restrictions do not necessarily impair computations, and you need to have a group of experts working in this area. I chose to concentrate on various cases of sharing data from different companies, sharing user data from different companies where privacy concerns are apply and privacy and sharing restrictions are taken more seriously. And it's very important, this last bullet, that alternatives are all bad. That you cannot, if you want to compute it in a way that is different than by cryptographic protocols, something will suffer. You will have potential points of failures or potential points of leakage, whereas with the cryptographic protocol, you will get kind of end-to-end security, in the sense that as long as a party holds its cryptographic keys secure, then its data doesn't matter if it travels through the protocol through other parties. Once you believe that the cryptographic key chosen by this party is secure and kept secure, then the data is kept secure. So that was important. And indeed, the setting is multi-company, which determines wide area network protocol with long communication. So communication minimization becomes first concern. And then you don't want too demanding communications either, because first of all, it will cause too much delays, and you may want to adapt it to other scenarios from the first solution. That was already a goal, that the solution is adaptive. Therefore, designed for possible extension, flexible component, multi-use, and things like this. And this gave rise to the private intersection sum problem. You probably saw it in the past. But it is good to see it again and get some perspective and see what was done based on the initial success. Because if you cannot in privacy technology, you cannot have a general enough solution. You cannot have specific solution for anything. You have to have a general enough solution that you can easily adapt for other things. And I will demonstrate this point in this. So, commutative encryption, due to the fact that we need to minimize communication, I looked at a private set intersection based on commutative encryption, which was designed by Polygon Hellman in '76, before RSA, exponentiate the cipher, and the exponent is the private key, and M to the P, M to the E1, mod P, this is the encryption. And turn out, as we know, exponentiation is commutative, and therefore these ciphers, once run in the same group, are commutative. So M to the E1 to the E2 is M to the E2 to the E1, and mod P, so FG is GF, these are commutative encryption. The order of exponentiation is not important, and this was noticed by Shamir in iCalc 80, that you can run using it secretly an equality protocol. And nowadays, of course, we can do it over elliptic curves, and we can prove its security, which is DDH. Therefore, sometimes people call this method the Diffie-Hellman method. And sometimes we use it only in the encryption side to find that ME2E1 equal ME1E2. And that's like a commutative joint hash rather than encryption, because we don't use decryption. Sometimes people call it, and this is one of the examples of what is known as oblivious PRF. These are more modern terminologies for this. But it's really, when I needed it, I had to go back to 1980, iCalc, which is not a typical conference where cryptography is being presented. I needed to be at my age to remember that this technique actually exists. And so based on this commutative encryption, we can do privacy preserving or private set intersection between G and M. G has a small g commutative encryption. M has F and then G takes its set of users, let's call them users, G1 to Gn, encrypt them with its encryptor G, send the list to M. M takes this singly encrypted list that was sent in one and doubly encrypted with its own encryptor F. So you get FG of G1 and so on, send it back to G in random order, and send it takes its own set of users, M1 to M sub M, and applies its encryptor F to this list, send it to G, and then G can take the singly encrypted list coming from M, apply G to it, and then check the doubly encrypted list of himself to that of doubly encryption list from M, and then find how many elements are in the intersection. So this gives the set size, and this is due to the random order on step 2 of the doubly encrypted list. But you can kill two birds with one stone here. If the initial list is sent to G in the original order without random order, then G can find the location of the doubly encrypted list. You can map those locations to the original element. So if FG of G1 the list, he knows that the first element is in the list. So this is a simple, as you see, it's linear the communication is linear in two sets, and that was the reason to go there, to this old thing. It's also something that is easy to explain. And to get a complete solution of what we needed, this intersection sum, we did a combination of commutative function-based PSI with something simple protocol called blinded sum that is also easy to explain. And it gave us a very communication efficient, scalable, and with parallelism protocol. Given optimization of the right parameters is important. The protocol is again between G and M. We add to M another encryptor, which was the Payet encryption that M generated. And then we can run the complete solution, the private intersection sum, in which the first part is running the G send its list, M. So now G is Google and has a list of users who watch certain content, and M has a list of users who spent money. M1 spent is S1. So Google sent its list of users encrypted. M doubly encrypt and permute this list. So FG of G1 and all. And then M sends its list of users, F of M1, but it attaches a Payet encryption of the spend of E1. And at the end, G doubly encrypts these elements from the M list, find the intersection by finding matches between GF of E1 and FG of MI, and then it can pick all the second component of those elements that are in common in these two lists, because the list from M carries as a tag Payet encryption of the spend value, so it can take it if it's in the intersection, multiply all these elements, multiply with random elements, gets a number, send it back to M, who has the trapdoor. M encrypts, it doesn't learn anything because R is random and big, and statistically hides the sum of the SI. It gets back the clear text, which is R plus S1 and SIs that are for elements in the intersection. And of course, it can subtract R and find the spend. And these calculations of how many people are joined and how much they spent on the average, these joined people, is very important for organizing this content campaign. Content being advertisement, coupons, and other possible tools. But the main thing is that nobody learns any individual element. G only learns how many are in the intersection and how much they spend in total. Of course, they reveal some upper bound because they can pad it with nonsense on the size of the original list of G of M, which are more or less anyway known. So what happened with this solution? So first of all, we did analytics of e-commerce between two commercial entities, keeping all user data secure. And then once the first group implemented it, and it was known that they don't do it otherwise, it was implemented in a number of cases. And variations of the protocol were implemented. This protocol is just one variant. There are other variants to it. And this runs routinely and brings analytics based on aggregate data. And it's really now in various systems. For example, you heard about Google password checking, where you want to know if your password is in a list of in a list of compromised passwords. So the technology to do this is also based on the private set intersection, in the sense that you can compute if your password is in the list without learning the list and without the other side learning what you found, because you can find it locally. So you see that this is again, it's kind of offline computation. It's not really real time, but it serves users. This was then open sourced as something that we call the join and compute, because you can think about intersection as a join in database and the sum computation. And then it was adopted for other things, but Facebook extended it to bridging identities, something that they were doing previously in an insecure way. And we extended it to malicious parties, which required theoretical work, and we published it in crypto. So we had a practical protocol based on the parties being honest, and we extend the protocol in a methodology that keeps the footprint of the honest parties to the malicious parties, and this way you gain efficiency in the malicious part. And as a result of things went beyond just Google. I think at least the big companies like Google, Meta, and other companies are now considering privacy enhancement as central to their business, and we hope to give more and in this domain of protocols like this. And in the future, I'll be able to talk about what we work now on. And the sentiments of 2007 that it's the end of crypto research is now, with a historical perspective, somewhat laughable. And, you know, it was, I think the end of crypto research was promoted from a point of view of self-interest, of people who wanted to say that their research is more important than crypto research. But that's the way to be right in the future. If you want to be right in the future, analyze the situation, try to analyze where the future of computing is gone, then predict. Don't predict to your research pocket, trying to convince funding agencies to give you money and not to others. But people with the history punishes those people. I don't want to say more about it, but definitely the thought that the game is just starting was more correct than those that thought that it's the end of crypto. Private computing groups with cryptographers and crypto engineers has become a reality in the industry. And also, by the way, our research showing the practicality of PSI, for example, gave a boost to PSI research, and I think we're going to see it in the next session. It's another reason that motivated me to talk about this perspective. I mean, what's nice is that this initial protocol and variants of are such that components of them were adapted and used for set intersection, for sum intersection, for size intersection size, and so on, for various applications. And once people saw the first system working and solving a problem that was considered impossible before, they wanted it. And what is the secret sauce or the takeaway from this? When you solve a fundamental industry issue, deployment will materialize. But things take time. You need patience sometimes. But if you know that you are fundamentally correct and everybody else is wrong, and you do it in the right way, just looking at your technology, maybe there are other technologies, and I will talk more about combining technologies in the sequel. If you do it right, you will deploy. And to do this, to know that you are working on a fundamental issue, you have to work closely with business, with engineering, and be mindful of needs. Another takeaway is that you have to be opportunistic. I mean opportunistic in the positive sense, which means deploy now, but you, as the designer of the security and privacy solution, think about extensions. And why is that? Nobody builds applications just to do privacy. They want other applications. So you have to be ready for demands of those applications. The fact that I knew that the first protocol did the sum and the intersection size, but it can also do that intersection, meant that when they wanted to do password check, which was intersection between a singleton group and a larger group, they can essentially use the same protocol. And this is very important. You don't have to tell anybody that you designed it like this. The need will show up according to your best estimates, and then you're ready. It's much better. much better than designing a solution to problem A, and then they come to you with a problem B, and you say you are not ready, you need to start research now. It's much better to have it already in software, tweaking an existing software and getting the solution. It's very important in the industry. So be opportunistic. If it doesn't cost you a lot, add hooks for future extensions as you see them. You always have to think about the future. You can never ride on the current success. The success is what comes next. And that was the important with this protocol, how we move to serve other protocols. In particular, password checking is an example of private set intersection. You have to adapt and know the cryptographic tools to other system requirements. You gain momentum, and you get more users, and you get more good name within the company. I'm talking now to engineers and scientists who work in industry. Be mindful of performance and system constraint and educate decision makers in a smart way. Tell them how it solves the problem. They understand much better performance than they understand cryptography. So if you can tell them the performance number up front when you run your benchmarks to yourself, it's much better. You're on a much solid ground if you know those numbers. Know your organization's unsolved issues. Don't let them, don't, you know, when we have a research problem, sometimes we go to sleep, we go to bed, and we are still thinking about them, how to solve them. So the same thing with industrial problem. They have to haunt you. And another thing which the bullet before last, I say crypto is elegant on paper, but in the overall system context, it is like security technology. It has messy components. It has other works that need to be done to make it real. And the final bullet is very, very important for security and crypto technologies. It's the foot at the door principle. Get an initial significant success, the rest will follow. This is very important. Work hard on the foot at the door principles, and then if you are opportunistic and you see the future, you will gain more success with the same or similar or tweaked technology, solving similar problems, and gaining momentum. So these are important principles, and this is why it was successful at the beginning, and this is why it is still successful in gaining new applications. Okay. Oh, we had publications in 2020 on this, but the publications just followed, and they were like the tip of the iceberg of all the work that was needed to get it done and get it done right and get the extension and popularize it and work on it inside the company, publicize it right, deal with the press that could not even describe it carefully, and so on. So my second example, so I switch gear and I talk about the issue of separating access from identity. And the issue is that Google One VPN was offered by Google for Android users. And the press reaction was laughing. Google now will track you there into your VPN. But the technical team working on the Google One VPN claimed it ain't necessarily so. So, quoting the Gershwin brothers. So, what happened? So VPN typically is like on the top you see unsecured connection to a website from the users. The user can be tracked. You know that this user and its IP address and so on are known to the website. And on the top, the internet provider knows things, and then there is the VPN connection in which the user has an encrypted tunnel to the VPN provider. So there are many users with encrypted tunnels to the VPN providers, and then there is a connection to the web. So you can think about it as the VPN masking the user from the website, and there's a crowd of users, and you don't know who accessed what. Essentially, the VPN provider hides the user, and the press claimed, Google is not fit to be the masking element for users against the website behavior and so on. But the technical team thought about a new architecture for VPN that will decouple the VPN provision from the knowledge of identity. And the idea is something like this. First, the user used its Google credentials and a blinded token to go to a Google authentication service. As a result, it gets a blinded token signed by this service. And this is property in which the authentication service send you a blinded token. And then the VPN clients at the front end of the user unblind this blinded token signature and says unblinded signed token to a key management service that gives it the public data, and now the service is taking place through the VPN tunnel, but the authentication is done at this stage, and at this stage it's without authentication because the authentication relies on the unblinded token and the unblinded signature on the token. So this is the model. And the initial deployment of the anonymous token was the old blind signing, employing the RSA blind signature tool, in which the user sent a hash of the token times a random value to the encryption exponent E. The server signed it, which is taking Y to the D, which is age of the token to the D times the random to the E to the D, which is just random. And this is the blind signature. And the user unblinds because it chose random, so it takes this value and divides it, so to speak, with the random, and gets a signature on the token. This is to remind you RSA blind signature, the first one that was proposed by Schaum and used by Schaum Fiat Nahor to implement offline coins. It is it's perhaps the earliest privacy preserving or privacy enhancing protocols involving three parties: the user and the authority that signs, and then the spending of the token. These days we have developed a few extensions. In a talk on this subject, I will talk about it. I could have presented extended scenarios. Other people in the company work on other tokens and other token scenarios, which are very nice. And the area of anonymous token in various other scenarios is really picking up in the industry for really various access scenarios in which you want to decouple the identity from the authorization to access. And I think it's a very important tool, and its time has come up due to the need to allow users to essentially hide in the crowd of certain services and not learning their exact pattern of access and what resources they access and things like this, which is an important part of user privacy. And what's the secret sauce here? First of all tools never die. And new adaptations may be dead, and the need for crypto tools may originate from other needs. In this sense, the fact that Google itself wanted to play the VPN tunnel provider, and we could not do it while hiding the user identity directly, and we need an indirect access. And another take is that privacy-enhancing technologies like blind signature plus the suitable architecture equals improved privacy. It's never the protocol alone, but within the right architecture, it's demonstratively gives improved privacy. And the old belief that authentication always implies lack of anonymity is not correct. And one more issue. It was really a joy to fit the existing theory to this problem. Kind of the glove was already, at least the initial glove already existed, and suddenly the right hand popped up thereafter. And this can happen, and one should not forget the existing flora of technologies that are available and adopt the right one. The example 3 that I'm going to give is token-free tracking in Internet of Things in the context of the Edison project or ephemeral ID project. It's a privacy solution for BLE devices, beacons, for the beacon ecosystem. And it's a design that has been since 2015, and this Bluetooth smart, which deals with small devices, simple battery-powered, low-energy hardware devices, similar to Apple Air. They transmit BLE signals. They are easily installed everywhere. And essentially, they are generic infrastructure to attach them to things if you want to connect them to smartphone and then through that to the internet, through that gateways. And these devices, they are tiny, they are broadcasting, so in this sense, they are like digital lighthouse that broadcasts in certain rate. It has some theoretical range. Examples of such devices are Samsonite Smart Suitcase, Fitbit, Tile, and other devices, and they can be a possible workhouse of some kind for the Internet of Things, because what I just said, you add them in some way to a device, and then the device has suddenly computing life. This is the example of the Samsonite suitcase. So it's real. It has a beacon, and this is the canonical example that we worked with. Beacon in a suitcase, and your phone, it's associated with your phone through an app. The phone scans regularly and identifies whether the suitcase is near you. It can alert you when you lose your luggage. Let's say the suitcase is not with you. It can alert you at the airport where the luggage reached the carousel coming off the airplane. Another case we wanted to support, though, is if the suitcase is lost and it went to another airport by mistake or something like this. And then it cannot be next to the owner's phone. This beacon can only be near other phones. We wanted the user to get an alert for where is the luggage. And this is kind of a global signal from anywhere to the owner of the beacon anywhere. Of course, it's beacons that can be attached to things, so not to be neglected, but also a need or a solution against abuse of beacons, which means I put a beacon in your car. I'm the owner. I will, using the global property, I will get signals and reports where you are. And of course, this is a major headache and it needs a solution as well. But the first three bullets are how to cope, how to allow operation, and the last one is how to prevent abuse. And you have to, often with solutions, whether they are privacy solutions or other solutions, you need to take care of both operation and anti-abuse. And that's the connection. If you look at the problem as it was, the fact that these devices broadcast, okay, encryption for security seems needed, so you can always get it and locally decrypt it, but point three, the global, the remote reach, it's out of range, it gets you to you through other phones. This seems problematic. And also, these beacons are battery powered and you need limited computing power. You don't want to waste a lot of computation. So the situation in itself look problematic. Nevertheless, we came up with a Eddystone EID, ephemeral ID, encrypted identifier that changes periodically in order to enhance privacy. And we need to take care of its security or privacy via cryptography. Hence the picture of Claude Shannon here. But we also need to hide or mask or randomize side channel by which different beacons are different from each other. And hence the picture of Kolmogorov here. So, what did we do? You share a key between the beacon and the owner, and then the beacon every once in a while, I will not get to all these details, but it starts to encrypt the time or the time window, and with this key, and therefore and send this as its identity. So the identity changes all the time, hence it's called ephemeral ID. And of course, to encrypt the ephemeral ID, we have to change the MAC address of the beacon, because it has a MAC address. Whenever we change the ID, we should change the MAC, and we should always encrypt whatever the beacon sends, the telemetry data, and so on. And then these are pseudorandom functions essentially, and the collection of pseudorandom functions is pseudorandom. So this will resolve cryptographically this problem. So what is this pseudorandom number good for? So locally, if you get this pseudorandom number that represents the ID, and the beacon is near you, and you are sharing the key with the beacon, you can immediately recognize that this is your beacon. But for the global situation, like the suitcase that is lost in another place, and another phone reads it, it cannot really decrypt it. So how do we do global from nearby mobiles to the owner through the cloud? Because the cloud needs to route it to the user, so we need to change the architecture and include the resolver in the cloud server, which employs the global reach of the cloud and its computing power as a trusted agent in a coordinated effort to allow to resolve and decipher the EID to the ID. So we essentially give this capability to this agent, and then we can get, here is the beacon on the left side. It sends an EID. If it's yours, your app can get it, the nearby app. Otherwise, if it's not yours, you send to the cloud. Here the cloud is, this application is depicted as run by Google, but it can be run by Samsonite, for example. and then you give the owner gives Google the ability to decipher ephemeral IDs, and then it can be resolved, and it can send you the original beacon message. So no, this is a BLE message. Here it's run over IP and can be less encrypted. And the resolver needs to route the signal to owner. This is problem one, and we enable it to get it. It doesn't need to know the info sent to the owner. The info sent to the owner, the encryption, is done with a different cryptography that is not shared, which is never shared with the resolver. The least privilege principle hold here. We needed to add end-to-end from the beacon, but also the phone nearby the beacon also reports certain information like location, and we needed a protocol between this phone and the owner phone without the owner and the phone never talking directly to each other. There's no interaction there. And nevertheless, we wanted to have this channel, and we solved it. This was done. This was part number 3. And finally, we need a trade-off between the remote beacon staying anonymous and the remote beacon potentially being abused to report location of someone else, a rogue operation. And this solution, there are solutions. Uh, they are under they are under development in the sense that they have to be programmed. And we also, the last problem, we need to solve the statistical side channel of differences in times of transmission between the different beacons. Because statistical behavior may also violate privacy. The deviations in time of transmission within the window may be a signature of specific beacon, and we wanted to mask that. So there was 5 or 6 problems to solve to make the privacy as high as we can and coping with abuse. What is the secret sauce? You have to know that new systems always have gaps, and you want to use cryptographic technologies, but it may not be enough. And you will need more analysis beyond the cryptography, beyond the just content protection. You may need architectural extensions to help you. This may present further privacy challenges. And always, new protocol opens the door for new abuse, and you always have to go from the design, the operational design, to the anti-abuse prevention design when you design privacy. Because you add privacy for operation, you may increase the power of abuse, you have to cope with it. These are principles, and you have to deal with them. At the end, the gain new functionality is important. So imperfect added privacy may be a goal due to various trade-offs. And you need to investigate the range of possibilities, and the perfect privacy sometimes is the enemy of the solid one. And here we had various problems. I didn't get into all these problems. I just mentioned how to do ephemeral ID with cryptography. I didn't talk about the end-to-end from the beacon. I didn't talk about end-to-end from the observer phone to the owner phone. I didn't talk about how you do resolution. There are various methods. And all together, suddenly it becomes a system in which the right information is kept private from the right agents. Nobody can associate old beacons with new ones because they change ephemeral IDs, and they cannot, and they don't have statistical characteristic of time of sending and typical side channels. You get end-to-end in the system, and the cloud trusted resolver know how to route in spite of the encrypted ID. And you put all these together and all these requirements, and then you add potential abuse when you are going to potentially stop worrying about privacy and start worrying about abuse and how you balance between the two. These are very important. So at the end, some solution with better privacy improves user experience and feeling and makes the system safer, but it will also take care of other things like abuse and the function of this. Without giving some power to the trusted agent in the cloud, we could never hear about the global suitcase that got lost and it is in another airport. So we cannot locate it. So I told you this started in 2015 and still ongoing because info security is a process, not a solution. And so is privacy. We are working and improve privacy all the time and on the right trade-offs. And here, this is what we have to learn from this solution. And also, again, things take time. And but we started very early. We started very early before any deployment of beacons has been already in the field. Okay. My example 4 is exposure notification using technology to help public health authority to fight COVID-19. At the beginning, I wanted to give a more elaborate protocol, but at the end, I settled for example 4 to be this due to some conclusions that we can draw from it. And it's important for the pets community, I think. So there was the pandemic, and we are technologists. And we are now in a world where we have smartphones that gives us online maps and services like Uber, mobile payments, and so on. What about health? And on the CDC, the Center of Disease Control and Public Health Procedures about pandemics, they were talking about contact tracing as an important tool containing the pandemic. And we had the BLE project, I told you, it is from 2015. So we gained some possibilities, some performance feasibilities and what BLE is capable of. And also, of course, other technologies that we examined for contact tracing, but in particular BLE, Bluetooth Low Energy. And the question was this: we have technologies, can they, not alone, but as another method in a bigger system? And not just can they help responsibly? We asked it in the company. Luckily for us, other companies and academia, also academic groups, started to, and health authorities started to investigate the question because apparently independently, and it was very very interesting to all. And we all realized the humanity status, back to my starting point, that human activities and computing are getting together, hence privacy. We are at the time where what I call Homo computatus, the computing man, is becoming Homo mobilis, the mobile phone man. And the question is, what is our ability at this stage? We have new computational model. We know that user data is handled with privacy, so privacy concern. We have utility, and what technology we want to use. And some personal realization for me throughout the project is, first of all, privacy is important. No need to give it up for each problem. If we start giving it up for this problem, then tomorrow there will be another problem. And then later on, when I spoke with the academic group that dealt with the same problem, and people in Apple, people felt the same way. People felt the same way. Yet, it is not a pure privacy problem. It's not a pure crypto problem. It's not a pure security problem. There were numerous constraints to get a product that can help in contact tracing. The productization of the ideas is hard. You need to take care of performance, usability, battery. Let's take battery. Suppose you have a solution, it depletes your battery very fast. So you see that your phone, that you, before you install the app that help you with the health, worked the whole day. Now, after 2 hours, you need to recharge the phone. If this happens, probably going to delete the app. And unless you live in a country where apps are mandatory, this will not work. Communication costs, constraints of BLE has to be taken into account. Usage, how usability and usage, and penetration in the market, because it's important to the big portion of the population will use the app to be effective. And how the server operates and the development time of this. If the pandemic lasts 2.5 years and development of the new product take 5 years, it's not going to help much. And of course, privacy, security, and safety also have to be taken into account. And these are all detailed technical issues. I just gave you the battery example. And constraints are interrelated, intertwined, and again, we'll see a trade-off here. And you need to run feasibilities on this, including security and privacy, threats, and so on. You need to check various designs and see what are the problems in principle. And someone's great idea may sit in an awkward place on a trade-off curve. Whenever your decision to come up with a product which is in a trade-off, there's not obvious, there's not an obvious optimal solution. Opinions vary, and you have to make your best estimates of all the constraints, and I listed here a lot of constraints, not all of them, but a lot of them. And you have to decide where to be the curve. You need feasibility study, which includes the privacy, but not in isolation. This is very important. Okay? Privacy does not leave alone. You have to confront it with the system function, the spec, with performance and usability, implementability, and trust in the issues. And here is the point. Much as I advocated before privacy by design, I want to refine this principle and say that it's privacy but by design, but not designed by privacy. Sometimes we have a tendency to follow a scientific paper about privacy and drive the design from it. It will be great, but it may not be the right solution. It's because it will be designed by privacy, where we have many constraints. So, what happened in the project? We explored various technologies, numerous BLE designs. So before BLE, we also examined other technology, but then we settled on BLE due to its better accuracy. But we looked at it from pure privacy. For example, I did privacy preserving contact tracing based on join and compute. What else? And more complete versions appear by other people. But I did it just to see the price. And we did design based on ephemeral IDs, only reveal IDs of infected people, revealing hash of IDs and so on, or keys and so on. This one alternative was to reveal the encryption key of the day, which gives you the most compression to if you work a solution based on ephemeral ID, if you give the key, you can regenerate the ephemeral IDs. But from privacy point of view, you can connect IDs in the day, and this is a trade-off. You can connect them. You can understand that the same person found in one time is in another time the same person. This, at the end, became the Google Apple exposure notification after much work by the companies, by academia, many engineers in many areas. The ephemeral ID envisioned as a layer for privacy is the key point in this design. The protocol is very simple. Have a key, have a random key for the day, 10 minutes, derive the next essentially ephemeral ID and broadcast it. Scan and read other IDs around you, and that's it. That's what you do. If you are infected, you need to report, upload the 14 keys of the last 14 days that you had, and every day download all published keys and check for exposure against all 144 daily IDs from each of those keys. And then you get how much exposure you had to these IDs and for how long, to deduce epidemiologically whether you have been exposed. And then, based on this, your phone is making locally the determination, and this is combined with other procedures in the real world. The health authority to run the app for you determine. And that's it. So the blue thing here is the API provided by the smartphone companies, and it was realized early on that it doesn't matter if you have iPhone or Android, smartphones is a smartphone, and you want to work together for the common good. And then on the phone, it will be determined your exposure. All right, so this is a simple protocol. And then when the protocol got published, the protocol got numerous criticisms from cryptographers who came up with many attacks regarding privacy violations. And it was good to, I'm not against scrutiny. In fact, I am pro scrutiny, and it's important that this were done. Yet, a principle that I already mentioned about architectures and cryptography is a layer, and there are many other protective layers. The Gaian protocol, in fact, does not run in the user space at all, but at the system space, as other manets protocol that you don't want the automatic network protocol to be based on the user wishes. So you put it on the system level, not at the user control. And then if the user tries to jailbreak the phone and interfere with the protocol, then the anti-abuse layer of the system space will interfere and will prevent it or detect. That's one thing. When I discuss those cryptographic attacks, I never refer to the fact that it's not just the cryptography. There are other layers that are helping it. We put it in the right place in the architecture. It's very important to locate things in the right place. Also, what attacks are done at a reasonable cost to the attacker is an important issue. This is the core of risk analysis. Not worst case attack like cryptography is doing. If I can find 5 people who are sick, find their identities, is it worth that I will pay $100,000 for it? If I can fool 10 people to stay at home when they don't need to stay at home, does it worth 200,000 people for me? It's not like ransomware when I attack something and I know I'm going to demand a certain amount of money, also done by the risk analysis of the attacker in order to assure that it gets the money. Then it has the right incentive to mount this attack for the right cost. And the secret sauce in this is the use of cryptography as part of multiple security technologies, not as a single layer. Physical security and hardware security modules can be employed, and the joint system together is the privacy enhancing technology. It's not just the protocol, it's not just the software layer, it's not just the algorithm. The algorithm is very simple, but designing the system, where to put what, all the other smartness and anti-abuse that there is already in the architecture, and exploiting them for the sake of giving enhanced privacy is important. You have to view it this way. It's very nice to have nice personal protocols. However, it is important to come up with system, and when you come up with system, you use all your resources. At the end, I did security analysis and exploration of the problem. So when apps were running, I teamed up with Virginia Tech based team, to do actual analysis of the phone with usual projects that is done in academia with students that are going to try to break phones, to look at phones, and do it. And essentially in this analysis that was published by an IEEE computer this year, we realized it is private to all but very extreme and costly attacks. And risk analysis techniques approves this choice of running the protocol where it runs and running these protocols. And also, 2 years or so running, no attack was noticed in practice. At least it was not noticed. And this is one thing, and this is due to this secret sauce of used cryptography as part of multiple security technologies. In a paper, you probably want to write a paper about a nice protocol. In a system, you want to add security measures to your protocol to cope up with added risks to the running environment of the protocol. So this is essentially what we found and we published. And it was good. It was good to have the attacks. It was good to have the scrutiny, but it was also good to have an evaluation of existing app, existing phones, Apple and Google, and investigate the risk in the real on actual system, on the actual systems. So that's one thing. Second thing, further, for secure analytic of the apps as a whole, researchers and engineers in Google and Apple built on the PRIO system, the ENPA, the Exposure Amplification Private Analytics. It was presented by Mariana Reichel from our team in Real World Crypto this year, to allow private computing by not revealing individual data, provided that the two servers performing this private computing are not collaborating. It shows that for the common good purpose, one could find independent servers to perform MPC and to be trusted. And the secret sauce is have a system with privacy. And when you need to add more computing on top of it, don't give up the privacy. Instead, build a private procedure on top of it, kind of modularly build privacy-enhancing technology, matching the privacy level. And this is how it's done. Users were contributing to
Moti, I'm terribly sorry, but we need to come to sort of a conclusion relatively soon, because I think people have lots of questions, and we only have like 5 more minutes.
Okay, so yes, so anyway, this was done, and let me conclude and say there is a need. Rest assured, there is a need for modern cryptographic technologies for privacy, namely PETs. It may come up in various systems and business, due to other constraints like legal and so on. If you want to deploy advanced cryptography, PET protocol, you have to explore it in this context, and usually it's initial customized technologies like join and compute. If it's done right, then it can gain momentum and be used elsewhere. It is quite rewarding to be involved in specifying, designing, and deploying of these. This is happening industry-wide now. It's always starting small, having hooks for extension, and then you can do it. I gave a few takeaways that you better take it into your heart. If you want to rely on my word and my experience, of course you can develop your own. It's very important that the leading company now recognize PITS. PITS was really a pioneering forum in this area. And finally, in many situations, adding privacy allows one to perform more computation under constraint and with respect to user, because otherwise it cannot be done. Hence, I will finish by saying that privacy technology is like car brakes. Brakes were originally introduced to allow cars, not to allow cars to stop, but to allow them to accelerate and speed up, and then stop safely, nevertheless. Before brakes, 30 miles, 25 or something miles per hour were the speed limit for car. And privacy has the same effect. It seems like it's blocking you, but it allows you more computing. So thank you very much.
That was a very nice conclusion. Thank you. Okay, so I wrote down 6 or 7